Contact-rich manipulation in unstructured environments such as warehouses requires robots to handle complex, uncertain interactions. The robot needs to reason about friction and contact dynamics that can be hard to accurately model analytically, especially when certain parameters are unknown.
For this reason, we introduced LaunchBot, a robot that excels at contact-rich manipulation that is relevant for real-world tasks. The goal of LaunchBot is to launch a box into a bin. The box can be of varying mass, and the bin varies in location. Because the robot must adjust to the task setup, and this can be difficult to do analytically, we present a reinforcement learning approach which adapts its trajectory from context forces and other variables.
To evaluate the generalization capability of LaunchBot, we define two task variations that introduce uncertainty in different physical parameters. The first task is mass variation, where the mass of the push boxes vary between 0.01 and 20 kg. In this task, the mass is not explicitly provided and has to be inferred. The second task is bin location variation, where the x-coordinate of the target bin is varied between 0.8 and 1.8 meters. Before diving into reinforcement learning, we first developed a physics-based baseline to give us a clear benchmark for what an analytical approach could achieve in our dynamic pushing tasks.
This is a system diagram of the baseline approach, which uses a diff-IK controller based on the Jacobian pseudo-inverse. We calculate the desired velocity of the push box when it leaves the table using the bin's x-coordinate as input by modeling it as a 2D projectile motion problem. We then compute the start and end gripper poses based on the table size and the box's start position. The intermediate poses are spaced between the start and end pose according to a quadratic schedule. Finally, these poses and timestamps are then provided to the diff-IK controller, which computes the joint commands.
Now introducing our reinforcement learning approach.
The algorithm takes in several observations from the environment, including the position of the robot, position of the box, and context forces between the robot and box. This is passed into a small neural network, which outputs a desired joint position. To restrict the search space during training, we only allow the RL agent to command 3 joints through a joint locking mechanism. This is passed into a PID controller. We train our model using proximal policy iteration, with a reward that is the negative distance between the box and the bin.
For the varying bin location task, the model is trained on discrete bin locations between 0.9 and 1.4 meters, and for the mass task, the model is trained on a small set of discrete masses from 0.01 to 15 kg. We evaluated the performance of LaunchBot by comparing it to our physics-based baseline across the two task variations. Performance is measured by success rate, defined as the rate at which the box lands inside the bin, and the average final distance from the target bin. We run each task for 100 trials where either the mass or bin location is randomly sampled. For the varying mass task, the RL performed slightly better with an 86% success rate compared to the baseline's 85%. However, for the varying bin location task, the baseline significantly outperforms RL. Let's take a closer look at each task. First, looking at the bin location task, the baseline achieves reliable success for bin locations between 0.8 and 1.5 meters. On the other hand, the RL policy only achieves reliable success for bin locations within 0.9 and 1.35 meters. However, this is still a significant and promising result for RL. Despite being trained on discrete bin locations, the policy was able to generalize for locations between these values. For bin locations less than 0.9 meters, the policy often fails to push the box off the table. It attempts a strategy similar to what works for 0.9, but starting from a position that is too close to establish effective contact. Beyond 1.4 meters, the RL policy shows a linear trend in distance from the target, and the push box lands at the same location regardless of the bin location. This is likely because the max location our model was trained on was 1.4 meters, and the policy failed to generalize for farther locations.
In the baseline controller, the end effector would deviate from the commanded path when given faster speeds. Sometimes the end effector would go over the box, either rotating the box or even missing the box entirely. We believe this is due to the physical constraints of the arm.
Now taking a look at the mass variation task. Both approaches achieve reliable success for masses up to 15 to 16 kg. The RL approach achieves occasional successes for masses more than 16 kg, as shown by the successful trials around 17 kg and 19.5 kg. Again, despite being trained on only a small set of discrete masses from 0.01 to 15 kg, RL is able to generalize and succeed even for masses between these values. Additionally, for masses above 15 kg, the policy still achieves occasional successes, indicating some generalization beyond the training distribution.
The baseline controller struggles on masses that are above 16.5 kilograms and the box falls short of the bin or does not make it past the table. However, the worst performance is expected since the approach does not account for the differing mass.
The RL approach also struggles on larger masses. One explanation is that the robot's range of motion is restricted by the joint locking mechanism. Better tuning of the reward function would also incentivize the algorithm to not enter a local minimum.
Even though the RL approach did not achieve the level of performance relative to the baseline that we had anticipated, our findings remain promising. The results indicate that the RL policy is capable of learning and generalizing across variations in task parameters to a meaningful degree.
Overall, LaunchBot successfully demonstrates that learned policies can adapt to varying object properties and target configurations. Future work may include adapting the approach to work with more joints and more dimensions, generalizing to more complex object geometries, and validating our approach in the real world.